Okay, I'm going to talk about the singular value decomposition of a matrix. Now, that's a very, very general purpose tool, right? So you have probably even perhaps used it before. These are tools that are available in any package worth its salt, right? But it's worth really understanding the geometric insights behind it, because they're very useful in even problem formulation in many settings. And secondly, of course, we are also going to apply it for dimensionality reduction via principal component analysis. So I first want to explain what singular value decomposition means geometrically for a matrix. So let me consider a matrix A, a generic matrix A with m rows and n columns. What is it doing? Well, it's basically, if I look at A times X for any generic vector X, of course that has to be, X has to be n cross 1, A is m cross n, and this A times X is m cross 1, right? So this matrix A is just a linear map from n-dimensional space to m-dimensional space. So that's what it is. It's just a linear mapping from n-dimensional space to m-dimensional space. And what we are going to try to understand is the geometry of this mapping via the singular value decomposition. Okay, so before deriving the SVD, let me state a geometric view of it. So remember that A is a mapping from n-dimensional space to m-dimensional space. I should also note that A transpose, which is n cross m, is a mapping from m-dimensional space to n-dimensional space. Now, you might know this, basically that the column rank of a matrix is equal to its row rank. What does that mean? It just means that the dimension of the space spanned by the columns of A is the same as the dimension of the space spanned by the rows of A, or so this is the column rank of A is equal to the row rank of A, but the rows of A are the columns of A transpose, so it's the column rank of A transpose. So you know this, and we're going to just actually, it will fall out of our derivation when we have that. So, but it's equal to something. Basically, it's the dimension of the subspace spanned by these rows of A or A transpose are the same, and let's say it's equal to R. Well, how many rows does A have? It has m rows. So, and how many columns does it have? It has n columns. So R has to be less than or equal to m as well as n. So R is less than or equal to the minimum of m or n, right? So basically, if you believe this row rank equal to column rank business, then there can only be, there's this subspace of dimension R that we are looking for in each direction, and the SVD actually tells us the structure of this subspace. So again, I'm just stating results now, not deriving it. So let me. So what that really means is the SVD is saying that I can actually find V1 through VR an orthonormal basis for the column space of A. So basically, the space of all possible AX. So what is the column space of A? It's the subspace AX. Remember what AX is, right? It's x1 times the column 1 through x. How many columns does it have? N columns, right? So xn times an, where x can vary over all all possible vectors, right? So and this has is a subspace of Rn and I'm calling its dimension R. R may be as big as n, but it cannot be bigger than the minimum of m or n, right? So I can find a V1 through Vr, which is an orthonormal basis for the column space of A, and simultaneously U1 through UR, which is an orthonormal basis for the column space of A transpose, and again that is just an analogous definition, such that there are these special pairs, such that when I send Vi through A, and I get, of course, A times Vi, that's going to be a multiple of Ui, and when I send Ui through A transpose, and of course I'll get A transpose Ui, that's going to be the same multiple of Vi. So essentially what I've found is there are these orthogonal modes into which I have decomposed A or A transpose. There are R orthogonal modes, R of them, where R is the dimension of the column space equal to the dimension of the row space. So that's what the singular value decomposition of a matrix is, and I can write it. Now, if I give you this, how do you tell me what A actually is in terms of these guys, right? So how do I write the matrix in terms of these V's and U's? I'm going to give them names in a minute. Well, you have specifying A is a linear transformation, is equivalent to specifying AX for all possible X. So basically, once you recognize that a matrix is simply a linear transformation, just specifying the transformation specifies the matrix. So let's see what we can do. So any vector X can be expanded in terms of an orthonormal basis, right? So what I can do is I can expand X with respect to the VIs. How do I do it? I project X onto VI. That's the projection onto VI. And I have then I multiply by the basis function, and I have only R of them, but if R is less than n, I can complete the basis by adding more components, right? So I'm gonna say that n of these VIs. So let me just clarify what I mean. So V1 through VR are orthonormal functions, defining those modes that we talked about, and then I just pick as many basis functions as I need, orthonormal basis functions as I need. I complete the basis. So these are also orthonormal, but they sort of complete the basis. But look, they are outside the column space of A, right? This is the column space of A. This span the column space of A. This means that A times Vi is 0 for I equals R plus 1 through n. So basically, if I'm having to complete it, that means that all of these other guys are going to contribute precisely nothing. So I have that, and now you give me a vector on which I want to apply A, and I expand that vector with respect to the spaces, and then I apply A, right? So I get summation I equals 1 to n. Linear transformation goes inside the summation. A times Vi, then Vi transpose X, right? And of course, A times Vi is sigma I Ui, I equals 1 to R. I can actually make it go from I equals 1 to N also by letting sigma be equal to 0, but let me just go with this for now. Sigma I UI VI transpose X. All right, so now we see exactly what A is. A is the thing that is operating on X. So we have just found the following representation for A in terms of the U's and V's. It's got R of these terms and then sigma I and then the outer product of UI and VI transpose. And so now, I mean, this is where the matrix form of SVD that you know and love, perhaps you don't know, that's fine. I would love it if you actually coming into this completely fresh. So I can define a matrix U, which has the U's as columns, U1 through UR. I can define a matrix V, which has the V's as columns. What are the dimensions of these matrices? Well, the V's are spanning, are part of a basis for n-dimensional space. So, in this direction, it is length n, and there are of them. So basically, this is an n cross R matrix. Similarly, this is an M cross R matrix, right? The U. And now I can see that this is equal to U times a diagonal matrix times V transpose. You should verify that, where D is just a diagonal matrix that has these sigmas along the diagonal. Sigma R, zeros, and of course, so this is R cross R. So just to verify that all these dimensions work out, you have M cross RU, R cross RD, and R cross N V transpose, because V was M cross R. So you can see that this is M cross N as you would want. So this is what you see. But what I want you to remember is the geometric interpretation that A, and I'm going to put it as equations now. A times VI is sigma I UI, and then A transpose times UI is sigma I times VI. And we have names now for each of these quantities. So these sigmas, these are called singular values, and the U's and V's are called singular vectors. The U's are called left singular vectors, and the V's are called right singular vectors, because they appear on the left and right respectively of the singular value decompositions of A. So left singular vectors of A and right singular vectors of A, and of course the left singular vector of A is a right singular vector for A transpose, right? Because if A is U D V transpose, A transpose is U D V transpose, which is V transpose transpose, D transpose U transpose, which is V, and D transpose is the same as D. It's a diagonal matrix, V D U transpose, right? So the left singular vectors of A are the right singular vectors of A transpose. So the SVD applies to arbitrary matrices A, right? But it looks suspiciously similar to the spectral decomposition of non-negative definite matrices that we've seen, and the reason is because they really come from that. So let me now derive the SVD. So SVD derivation related to the spectral decomposition. So let me look at AX for an arbitrary vector X. Let's look at the size of this. So the L2 norm squared of that. What is that? It is AX transpose AX, right? Which is X transpose A transpose A times X, right? And so I can see that there is this matrix that is appearing here. Let me call it W. And this W is actually non-negative definite. So this is non-negative definite by construction, actually. Why? Because this is bigger than or equal to 0 for any X. So that means X transpose WX is bigger than or equal to 0 for any X, which is the definition of a non-negative definite matrix, right? And so now let us define. So it has its eigenvalues are non-negative, and suppose it has R strictly positive eigenvalues. And so let me solve them lambda 1 through lambda r, and then there's a bunch of zeros, so 0 eigenvalues, and then corresponding eigenvectors are those v1s and vrs that we are talking about. So these are all bigger than 0, and of course, let's go back and look at the dimension of W, right? So A was let me change pen color again. So A was M cross N, so A transpose A is N cross N, right? So because I am multiplying an N cross M matrix with an M cross N thing. So basically I have W is N cross N, so this R is less than or equal to N, the entire dimension N. And of course, as before, we can complete the spaces up to N as we like, but it's not going to make much of a difference. So what I have is the spectral decomposition of W like we had before. W is taking only the non-zero or strictly positive eigenvalues. It's lambda I VI transpose, which I can also write as V lambda V transpose, where lambda is the diagonal matrix of eigenvalues, right? And where basically this has R columns, V has R columns, right? V is V1 through VR, so it's an N cross R matrix. Of course, remember we have, of course, normalized these, so these are orthonormal, right? Some of these eigenvalues may be repeated, but then you can always orthogonalize the eigenvectors, and so basically these are orthonormal. And now let me just define U to be whatever will make things work. So what let me define UI as some constant times A times VI, right? And let me look at what and let me look at what I need to do to normalize things, right? So let me look at UI transpose UI. Let me give abbreviate this constant. Let me call it CI. Okay, UI transpose UI. This is the norm squared of UI. I want this to be 1, so it's going to be CI squared VI transpose A VI, right? I'm just doing the same, just plugging it in, right? And so what do I have? It is Ci squared Vi transpose. A transpose A is just this W times Vi. And so this is since Vi is an eigenvector with eigenvalue lambda I, this is lambda I times Vi. So I get Ci squared lambda I Vi transpose Vi, and of course this is equal to 1 because I have normalized them already. And this, I want this to be equal to 1. The energy of these UIs I'm going to normalize to 1. What does it tell you? That Ci squared is going to be 1 over lambda I, or Ci is 1 over root lambda I, which is fine because lambda I is strictly positive. So I am defining the UIs as 1 over root lambda I A times Vi, right? And so inverting this, I mean, remember I had this idea of Vi going through A and giving me sigma I Ui. So what do I get? A times Vi is root lambda I times Ui. And so this is what I'll set to my as sigma I, right? This is my sigma I. Okay. The other thing is I have constructed these V's to be orthonormal, but I want these U's to be orthonormal as well. So I want to just check, are they orthonormal or not? So let me just do the same calculation. So I've just said this is what I need to normalize U. These are normalized to unit norm. Now let me just look at the inner product between two of these guys, Ui and Uj, right? For I not equal to j. So what is it? It is 1 over root lambda I A Vi, that's Ui transpose. I have to transpose that, and then 1 over root lambda j A Bj, right? And so that is Vi transpose A Bj divided by root lambda I times lambda j. I'm redoing some calculations that I could have avoided, but that's fine. And A transpose A is of course W, so I have Vi transpose W operating on the jth eigenvector of W divided by root lambda I lambda j. And now this guy of course is lambda j times Bj. So I get lambda j over root lambda I lambda j Vi transpose Vj, and of course this is equal to if I equals j, then this is 1. This is I've normalized the Vi's to unit energy, and then you get lambda I over root lambda I, so it's 1 for I equals j. We had already shown that, but Vi and Vj are chosen to be orthonormal, so it's 0 for I not equal to j. So we have the U's inherit the orthonormality of the V's. What about the other direction? We had promised that it would work in the other direction also. So again, I keep drawing this figure over and over again. Vi going through A give me sigma I Ui. Now let me. I want to see what happens when Ui goes through A transpose, right? Okay, so basically, remember what Ui was. Ui was equal to 1 over, I'm going to go back to that definition we had for normalizing things, 1 over root lambda I times A Vi. I'm going to apply A transpose to Ui, see what happens. I get 1 over root lambda I, A transpose A Vi. Remember, that's the matrix for which I had done the eigen decomposition in the first place. So W times Vi, and of course that is equal to, let me change pen color. that is equal to lambda I times Vi, and so this is root lambda I times Vi, which is sigma I Vi. So I can complete it happily and say, okay, this is sigma I Vi. So I have just shown you that by defining the appropriate non-negative definite matrix, I can do the eigen decomposition of that, and that gives me the singular value decomposition for the original matrix A. So now, given this background, it is fair to call these guys the eigenmodes or eigenmodes of A or A transpose. They come from the eigen decomposition of the matrix W. So now we can talk about the geometric interpretation of what the SVD is. So, just like you have vectors that have certain sizes along different dimensions, right? So if I have a vector in d-dimensional space, its L2 norm is I square up the I square the entries, sum them, and then take square root, right? And that's my my L2 norm of the vector. For L1 norm is I take the magnitudes and add them up. And these dimensions that I'm talking about are basically just the basis, the directions in which I have defined my basis for my d-dimensional space, right? That's how it is. Now, what the singular value decomposition does for a matrix is it decomposes into R directions, R essentially orthogonal directions, independent directions in operator space, right? SVD decomposes A into R directions or eigenmodes, and I can have actually exactly the same kind of definitions for norm as I had for vectors. So that's the key idea here. The names, unfortunately, are not quite going to match, right? So I'm going to write down some things. So what is the L2 norm of a matrix A? The way we define it and the way we denote it is it's the if I apply A to X and look at the size in the L2 domain and divide by the norm of X, and I take the maximum over all vectors X not equal to 0, right? So that's what my L2 norm definition is. I mean, I could also write it as the max over all X which have unit L2 norm of the L2 norm of AX. It's pretty easy to see that this is going to be exactly equal to the biggest singular value, where without loss of generality, I'm going to order them in decreasing order, right? So this is pretty easy to see because any vector can be decomposed into this, with respect to the orthonormal basis V's, and clearly putting all your eggs into the biggest basket is going to maximize this quantity. So the L2 norm as defined here is more analogous to the L infinity norm of a vector, right? So the L2 norm of matrix is defined like that. What is analogous to the L2 norm of a vector? Well, that's the so-called Frobenius norm. So how would you define the Frobenius norm if it were the if it were the analog of the L2 norm for a vector? Well, the Frobenius norm is going to be the sum over the squares of the singular values, right? And you might actually have seen a different expression for it. So let's actually see what that boils down to. So basically, this is equal to the summation over I of the lambda i's for the matrix W, which was A transpose A. And now I should remind you that the sum of the eigenvalues of a matrix is actually the trace of the matrix. So this is the trace of A transpose A. So sum of the diagonal elements. Well, what are the diagonal elements of A transpose A? They are just A transpose A is A transpose ij times A ji is the ith element of A transpose A, the ith diagonal entry. I'm going to sum, if I sum it over J, of course, and then of course I have to sum over the diagonal entries to get Ij here, and of course A transpose Ij is Aj, so I basically have Aj squared. So basically this is this is actually, the Frobenius norm squared. Just like the L2 norm squared is the sum of the squares of the entries, the Frobenius norm squared is the sum of the squares of the singular values. And so this is basically the sum of the squares of the entries of A. So that this is what you might have seen. This is what you might have seen as the Frobenius norm, but really in terms of our geometric interpretation of the sigma i's as sort of the projection of the matrix along these eigen directions, eigen modes, this is the thing that directly establishes the analogy to the L2 norm of a vector. So let me just, since I've sort of made a mess here, let me just summarize this. This is equal to summation I sigma I squared. There are only r of those terms that are non-zero, and then summation I lambda I. This is for the W matrix. W is because it's often called, in a specific context, it's called a Y-short matrix, but I don't want to dwell on that. And of course, it is the sum over I, sum over J of all of the entries of matrix squared. Right, so that's the Frobenius norm, and this is really the part that I wanted to emphasize as the analogy of this. Okay, so we have the L2 norm of the matrix, which is analogous to the L infinity norm, the Frobenius norm of the matrix, which is actually analogous to the L2 norm of a vector. What about the L1 norm? Well, that has its own fancy name. It's called the nuclear norm of A, and so the notation for that is A with this star, and that is simply the sum of the magnitudes of the entries. All these entries, meaning the sigmas, are positive, right, or non-negative if you allow for the zero singular values also in the summation. That is just the sum of the singular values. So that's the nuclear norm. And we'll see that just like the L1 norm is often used to enforce sparsity, the nuclear norm can be used to enforce sparsity for a matrix. So what we'll see is, when is a matrix sparser than its inherent dimension? When, for example, its row space or column space has effectively small rank. So in fact, I should say that the rank of a matrix, so rank of A, while I'm about it, is the number of, so I'm going to, rank of A is the number of non-zero singular values, right? That's basically the dimension of the row space or column space. So this is the rank of A, which is also equal to the rank of A transpose, and this guy is analogous to the L1 norm of a vector. And this guy, of course, there's a number of non-zero entries, so it's analogous to the L0 norm of a vector. And typically, what we'll talk about is, when we talk about sparsity, we talk about of a vector, we talk about small L0 norm, small number of non-zero entries, and we often relax this constraint in terms of the L1 norm. Similarly, we might have constraint on, basically sparsity constraint on a matrix, which we want to say that the rank is small, but we might relax it and talk about it in terms of a nuclear norm, because it will turn out that we can, optimize things better there because of some certain convexity properties. So all those things we'll touch upon later. One more general statement I want to make about the SVD is its role in low rank approximation of A. Basically, it's just pretty easy for us to see, because these VIs that we have in the SVD, they are orthonormal, that we can come up with a successive decoding kind of, if you want to call it that, method for getting the SVD. So remember that sigma 1 is the max, and I'm going to actually put V here, over V, such that norm of V equals 1 of A times V, right? That's basically the analogy, and this is the so-called L2 norm of the matrix, which is more analogous to the L infinity norm of a vector, right? So that's sigma 1. It's pretty clear that sigma 2, now that I've found and also, by the way, let me say that V1 is sort of the argument of the max there, right? Of V2 equals 1 AV. So basically V1 is that guy. Now that I have V1, I can get sigma 2 and V2 as by maximizing over V, such that V is orthogonal to V1 and has unit norm, the same thing, AV. And this will give me sigma 2 and V2. And we can keep going this way to get up to however many non-zero singular values we have. And so we, if you tell me, if you ask me to give you a low rank approximation of A, so minimize over B such that, say, rank of B is less than or equal to some R hat, say the Frobenius norm of A minus B, the answer is actually going to be exactly the SVD truncated at R hat. So B is going to be summation I equals 1 to R hat. Let's assume R hat is less than or equal to R to avoid triviality. Sigma I UI BI transpose. I mean, it's pretty intuitively plausible, and I'm not going to prove it, but it's pretty clear what the role of a low rank approximation, what the role of an SVD is in providing low rank approximations. And that's what we apply when we do principal component analysis of a bunch of data.